Cybersecurity is one of the fastest growing and most respected fields today, and earning your CISSP certification can open the door to some of the highest paying and most trusted roles in the industry. But passing the CISSP isn't just about memorizing facts, it's about understanding how to think like a security leader. That's exactly what this course is designed to do. I will walk you through every domain, simplify complex topics, and share real world examples that will help you not only pass the exam but truly master cybersecurity. So, before we begin, like this video, hit that subscribe button, and turn on the notification bell. Welcome to our last domain, domain number 8, software development security. So this is a short domain but important one. So let's get started. What is SDLC, that is software development life cycle, and why security matters in SDLC? So SDLC is an iterative process to develop, update, and improve software based on the user or customer needs. So the phases in SDLC follow a logical order, such as initially in the first phase, we gather the requirements, then we design the system, then the actual development of the software through coding, then testing, and then deployment of the software or application in production environment. So security must be integrated in every phase. So that is the important point, but not added at the end. So security should be included from the very start, that is during requirement gathering, and must be included in all subsequent phases. So the CISSP role in SDLC is to define security requirements, guide developers, and ensure secure design and testing. So CISSP does not or do not need to do the actual coding or develop the software, but to define and look for the security requirement in the development. So we need to distinguish between SDLC, which deals with the development of the software, from the SLC, which is software life cycle, which is the full system life cycle that also includes the operation of the system, the maintenance, as well as the final disposal. So what are the core software development life cycle phases? So the first one is the initiation, where we define the business need for the development, we document the requirements and approve the resources from the management. Second phase is the actual development, where we design the architecture, actually create the code, and integrate the purchased or external component if there are any. Then we finally deploy or deliver the product. So in this phase, we release system into the operational or production environment. We perform the functional and security testing. And then we have the operations and maintenance, which is an ongoing process. So during this phase, we regularly apply patches, apply the updates to the software as per the requirements, and we do all the patches and updates as per the change management. So SDLC can restart when requirements evolve. So if there are requirements, new requirements that should be integrated into the system, then the whole process of SDLC again restarts. And the final phase is the disposal, which is the secure decommissioning. And during decommissioning, we need to migrate data from the decommission application to archive data if required, sanitize the media and the application, as well as the secure media handling. So now coming over to software development life cycle models, how do we develop software through different methodology or through different software development life cycle models? So the development methodologies include the waterfall. So the waterfall is a linear and strict phase completion. We will study waterfall in detail in upcoming slides. Then we have the prototyping, which works in iterative manner. It is basically improves the application based on the user feedback. So we get feedback from the user, then iterate the process and improve it. Then we have some modern approaches such as Agile and DevOps. So these are continuous, flexible, and they give incremental updates to the software in short phases or short circles. We will study these in upcoming slides as well. So first of all, the waterfall model. So what is the waterfall model? So it is one of the oldest SDLC models. It is sequential, that is, it is in an order, and it is non-iterative. Non-iterative means that we cannot go back from previous phase to the from current phase to the previous phase. For example, if we have these phases: requirement, design, implementation, testing, development, and maintenance. So this is a one-way traffic. What does this mean? This means that you go from this phase to next phase. But let's suppose if at testing you discover that there is some issue with design, you cannot iterate or you cannot come back to this phase. So you can say this is a very rigid and non-iterative model. So the progress flows in one direction, that is from start to the end, and there is no going back once phase is completed. So you cannot go from development back to the testing. So it works best when all requirements are known upfront or at the beginning, and the requirements are unlikely to change. So these are important points to consider and remember. So this is, as we studied how the waterfall model is. Let me clear this. So as we can see, this is a one-way process. It is called waterfall model because if water flows, let's suppose here, this water cannot go back naturally. So that's why this is named after this natural phenomena. So we cannot go from this current phase to the previous phase. So what are the pros and cons of the waterfall model? So the advantages include that it implements strict documentation and formal processes, and it has the strong support for security requirements and thorough testing, and it has the predictable schedule and deliverable because we know all the requirement upfront, and we know that in how much time we will deliver the product because there is no change of requirement during the development or after the project development is started. So limitation or cons of waterfall include that it is highly inflexible, it cannot handle the changing requirements, it is poor fit for modern dynamic systems and fast changing security needs, and it has the risk of delivering a system that no longer meets user need by the end. So if you go through all these phases, and let's suppose if you reach the end of the phase where you finally develop the product, the user requirements may no longer be met by this product because no user input was included during the intermediate stages. So then we have another model that is Agile. So what is Agile? So Agile was created by Agile Alliance in 2001 as a flexible alternative to rigid models like Waterfall. So it is based on the Agile Manifesto's 12 principles. So these are guiding values or principles and not a strict methodology. So the Agile basically emphasizes early and continuous delivery of working software, and it is designed to adapt quickly to changing business and security requirements. So it is, you can say, exactly opposite to the waterfall model. So key agile principle include deliver early and continuously. So it supports availability plus faster security feedback, welcome changing requirement. So it easily incorporate new security control, for example, encryption and validation. It has the iterative development, so smaller releases reduce risk and allow frequent reassessment of the threats. So in waterfall, we deliver the big final product at the end. While this agile model, it has the iterative development methodology where we releases small updates or development frequently. So cross-functional teams, so this requires security involvement in the requirement, design, and testing. Agile testing approaches, so testing is integrated, not as separate late phases like a waterfall. So in waterfall, we have a phase at the end that was testing, while in agile, testing is, you can say, integrated and it is included from the very beginning. So automated testing improves speed, consistency, and early detection of bugs and vulnerabilities. So each iteration includes lesson learned plus updated security requirements. So the goal is to prevent defects from reaching production through small, frequent, and testable changes. Agile development methodology. So as we said that agile itself is not a methodology, it is a manifesto or guidance. So based on agile, we have different development methodologies. So agile principles are implemented through various methodologies, and common agile based methodologies of SDLC include XP or extreme programming, test driven development, TDD, and Scrum. So we will study these one by one. So first is the extreme programming or XP. So in XP we have cross functional teams, that is we have the teams comprising of developers, customers, and managers. So uses it XP uses user stories and value based prioritization. It gives the value to the user feedback and user let's say recommendations. So the pair programming improves code quality and oversight. So in XP we have pair programming. What does this mean? This means that there is a developer, one person develops the code while the second person reviews the code, manually reviews the code. So this improves the code quality and also includes the oversight. Refactoring removes obsolete or redundant code, which reduces the attack surface. So in XP, we have the refactoring, which removes the obsolete or unused code. In this way, it removes or reduces the attack surface of the application by removing the unused or function or security code that is not required. Then we have the test driven development, TDD. So in this method, the methodology is to write the test first and then write code to make the test pass. So this ensures clarity on expected functionality. So it is useful for security fixes, for example, patching buffer overflows and injection flaws. And this methodology minimizes unintended changes in existing systems. Then we have the next agile methodology, that is Scrum. So in Scrum, we have some key roles. First is the Scrum Master. So the Scrum Master basically removes the blockers or you can say obstacles in the project and facilitates the processes. You can say it is just type like a manager that overall provide resources, facilitate processes, and removes any impediments. Then we have the product owner. So the product owner basically represents the customer and manages the product backlog. And then the actual development team. So this team includes the developer, the architects, the quality assurance team, and security testers. So we have these artifacts in the Scrum. We have the product backlog, which includes all the requirements of the project or the and you can say application, and these are prioritized by value. So we have all the requirements and their priority is such that they are prioritized by the value of these requirements to the system. Then we have the sprint backlog, which are selected items to be completed in the current sprint. So sprint, or you can say it is these are cycles. You can say the iterative processes during the overall development project, and the sprint are short term. You can say phases, for example, 2 weeks, 4 weeks, or 2 months. And the spring backlogs basically include the requirements or the items that need to be included in that specific sprint. What are the core activities in Scrum? So these include the sprint, which is the fixed time box, for example, 2 weeks to deliver the working features. We have the sprint planning, which is used to select the backlog items during this sprint. Scope should not change mid-sprint. So when we select the item that will be completed in the sprint, then the scope of these items should not change during the middle of the sprint, because again sprint is the shortest you can say a runtime or a phase, so you cannot just change requirement in the middle of the you can say 2 week duration. Then we have the daily scrum, which is the quick stand up for the current status and the blockers. Then we have the sprint review, which is the demonstration of completed work to the stakeholders, and retrospective, which include lesson learned plus improvement for the next sprint. Our next topic is the DevOps. So DevOps integrates development plus operation plus quality assurance into one collaborative team. So DevOps solves issues from siloed handoffs. It improves communication and delivery speed. DevOps uses automation, frequent testing, and continuous integration, continuous deployment, that is CI/CD pipeline. So the goal of DevOps is to deliver software faster without sacrificing on the security. So how do we implement security in DevOps? So the QA defines success criteria early and provides quick feedback via automated tests. So the emphasis here is on automated tests. So the tests in DevOps are automated, and so when the tests are automated, it means we can run these tests frequently and during each phase, and they provide quick feedback. So automated security testing helps detect vulnerabilities earlier. They reduces bugs reaching the end production system, and they speed up the patching. So security must be embedded in every stage of the pipeline. That is, security should be built in. Faster software delivery must not bypass security control. So the DevOps basically delivers fast delivery of software, but again, the security control and security needs should not be bypassed or compromised. And for this, we have the integrated automated testing of the security controls. What is the governance and access control in DevOps? So DevOps roles often hold privileged access, such as changes to the production system, user creation, and logs. So these are the access that the DevOps role has. So this requires strong controls. For example, the roles must have least privilege, separation of duties, and multi-factor authentication due to these privilege action that these roles can perform, as well as the monitoring. So automated tools must validate, test before the deployment of the application, and developers can mark code ready, but another role must approve the deployment. As we said, this is known as the separation of duty. So one developer can mark the code ready, but then there should be another role that approves this code. The developer should not be able to mark the code ready as well as approve it. Our next topic is DevSecOps. So DevSecOps integrates security into every phase of DevOps pipelines. It means security at the DevOps speed. It delivers working security controls now improved continuously and prevents delays caused by seeking perfection. So security becomes a shared responsibility across development, operation, and security teams. And it uses automation for code scanning, configuration checks, compliance, and vulnerability testing. What are the core principle and security comes of DevSecOps? So the real world testing focus, DevSecOps has the real world testing focus. It means that the red blue team exercises are preferred over theoretical scans, and it has data driven decision, not fear, uncertainty, and doubt. That is hard fear, uncertainty, and doubt. And there is continuous collaboration across all roles. So the result are fewer vulnerabilities reach the end production system. We have faster and safer deployment with integrated continuous integration and continuous delivery security checks and actionable risk insights based on actual exploit testing. So there is no single standard. Organizations adopt DevSecOps to meet their environment. Our next topic is the maturity models. So what are the maturity models? They are framework used to measure the organizational capability and guide continuous improvement. So the maturity model basically provide a baseline, a target state, and a path for improvement, that is process refinement. Higher maturity means formal, repeatable, and well managed processes versus ad hoc or chaotic ones. So, if we have ad hoc or chaotic processes, it means we have the less maturity. On the other hand, if we have formal, repeatable, and well managed processes, it means the organization has higher maturity level. So the maturity models are applicable to software development, security operations, and service-based IT environments. So common maturity model components are CMM components. So these includes the domains. So these are the functional areas the model actually measures. For example, the measurement, analysis, and documentation. Each domain contains defined practices such as how metrics are collected and how often they are collected. Then we have the CMM maturity levels. So maturity models use progressive levels, often from 1 to 5, showing the increased capability. What does this mean? This means that level 1 has low capability while level 5 has the highest capability. So each level has evaluation criteria used by internal teams or external auditor to determine the current maturity, and levels may apply to individual process areas or to the organization overall. So we may apply the maturity level either to individual areas or to individual processes or to the overall all the processes of the organization. Then we have the criteria. So to reach a certain level, an organization must meet all the required practices for that level. So lower level basically focus on basics ad hoc, that is the documented processes, and higher levels introduce advanced practices which are basically metric driven analysis and continuous improvement. So some models assign maturity by domain, others assign maturity per level across all domains. What are the targets? So the target maturity level is the desired state based on the business goals and cost benefit trade-off. So higher maturity reduces risk but also increases cost and complexity. So the targets help perform gap analysis and prioritize the improvements of the organization and the required processes. So in some industries, for example, the government contracting, certain maturity levels may be required. So they may be required by the laws. For example, some government agencies or government may require that the contractors may have certain level of maturity. For example, let's suppose level 4 for them to be able to work with the government. Capability maturity model, that is CMM. So this was developed by DoD, Department of Defense, and Software Engineering Institute of Carnegie Mellon University to evaluate and improve software development quality. So this was created in response to poorly managed and unpredictable software projects in the 1980s, and it was originally designed to assess government contractors' capability, that is on time and on budget delivery of the contractor projects, but its success led to adoption across broader business and development processes. So, capability maturity model integration, that is CMMI. So, evolution of CMM to it is the evolution, CMMI is the evolution of CMM to unify and expand maturity modeling across business areas. So, it has different versions, including the CMMI-dev, that is related to development or deals with development, CMMI-SVC, that is services, and CMMI-ACQ, that is acquisition. So CMMI is now managed by the ISACA's CMMI Institute, and it supports agile and cyber maturity programs. What are some CMMI maturity levels? So CMMI has 5 maturity levels. First one is the initial, which is ad hoc, unpredictable, and reactive. In manage, we have project level processes, but they are inconsistent. Third level is defined, where we have organization-wide proactive processes. Fourth maturity level is the quantitatively managed, where metrics are used to measure and control the processes. And fifth and the last maturity level is the optimizing, where we have continuous improvement using lessons learned and the analysis. OWASP Software Assurance Maturity Model, or SAMM. So what is Software Assurance Maturity Model? So it is a prescriptive OWASP framework for building and improving a software security program. It integrates security activities into the existing software development life cycle, and it is not a replacement of the SDLC itself. So SAMM basically provides a map, a roadmap. It assesses the current state and then defines the target maturity, then implement the improvements across processes, people, knowledge, and tools. So the structure of SMM is that it is organized into domains and each split into security practices. So each practice contains two activity streams. For example, the automated versus manual testing responsibility. Practices have three maturity levels, progressing from basic to fully integrated security activities. So we have the SMM domains and security testing examples. So software assurance maturity model domains include governance. So governance includes strategy and metrics, policy and compliance, and education and guidance. Then we have the design domain, which include threat assessment, security requirements, and security architecture. Then we have the implementation, which includes secure build, secure development, and defect management. Then we have the verification, which is include architecture assessment, requirements, driven testing, and security testing. Finally, we have the operations, which include incident management, environment management, and operational management. So security testing maturity level example, for example, in level 1, we have basic manual plus automated testing to find the defects. In level 2, we have more complete testing using the automation plus casual manual pen testing. In level 3, we have the security testing fully integrated into development and deployment pipelines. Our next topic is O&M, that is ongoing security controls and maintenance. So we have the vulnerability and patch management, which is an ongoing O&M process. It includes regular scanning for flaws and prompt remediation of these flaws, including patching the operating system, application, and sometimes triggering new software development iteration for custom code. Then we have the access control management. So this includes user provisioning, review, deprovisioning for the operational systems. And the production environments have far more users, so strong access governance is vital. Then we have the change and configuration management, which include controlled processes for requesting, reviewing, approving, and applying changes. And this ensures that system maintain a secure and known baseline. So maintenance activities include hardware replacement, operating system upgrades, and end-of-life migrations. Schedule maintenance windows to minimize the downtime. Regression testing after changes to ensure no unintended impact. So regression testing is always done after some changes to the application of our software to check that the change has no unintended impact on the functionality or operation of the overall system. Our next topic is integrated product team or IPTs. So what are IPTs? These are multidisciplinary teams comprising of users, customers, developers, contractors, and security teams. And the goal is to deliver product faster and with higher quality through collaboration and shared responsibility. So the IPTs were originated in the US Department of Defense for complex system development. And the benefits of integrated product teams is that they remove traditional delays by having all the key resources available early. It improves communication, reduces rework, and increases the speed of delivery, and ensures security requirements, for example, compliance and controls, they are addressed from the very start of the project development. Software development ecosystem and language security. So why software security matters? So developer relies on languages, tools, and environments. and each of these introduces risk requiring security controls. So security testing tools such as SAS, DEST, or IAST tools, we will study these in a while. They increasingly integrate into the software development lifecycle and provide continuous feedback. So CISP are certified information system security professional need broad understanding of the SDLC processes. They should not be coding expert. They do not need to do the actual coding, but they should understand the process to identify risk and required controls. So the programming languages include compiled languages such as C and Swift. So the compiled languages basically they are compiled to the machine code. They are faster and platform specific, and they have the capability to protect the source code. On the other hand, we have interpreted languages such as Python and JavaScript. So these are executed, or the source code is executed at the runtime. They are portable, but they also expose the source or source code. So we have the intellectual property or integrity risk, such as mobile code tampering. Then we have the database languages. So these include the SQL, and inside SQL we have DDL, data definition languages that define the database, DML or data manipulation language which query or insert the data into database, and DCL, data control languages that is used for the access control of data inside the database. So the security impact is that database access control and SQL injection risk. So then we have the type checking, and inside type checking we have the static type checking that detects type error at the compilation time, and this improves integrity. Dynamic type checking validates types at the runtime. This is more flexible but may fail later. Then we have the strongly typed, which is safer for data integrity, and weakly typed, which is again flexible but riskier. So programming paradigms, so we have the declarative, which is the SQL that state what to do and system handles how to do it. So the security is via abstraction and the access control. Then we have the imperative or procedural paradigm, which is step-by-step command and uses subroutines for consistent access control checks. And lastly, we have the structure programming, which include logical blocks such as if-then block, and it is easier for security review. Then we have the OOP security or object oriented programming security. So we have in OOP the encapsulation, which hides data and restrict direct access to data, which result in integrity protection of data, inheritance, which reuses the secure methods and control across subclasses. Then we have the polymorphism, which uses the same interface but have different behavior, and it may introduce logic misuse risk. Polyinstantiation include or has the multiple version of objects for different clearance level, and this prevents parents attacks. Next, we have the markup and scripting languages security, and these include the HTML and CSS, which include the structure and style and generally safe but can facilitate the injection. Then we have the JavaScript, which is high risk because it include the mobile code as well as the browser, since it is executed inside the browser. So if we have the mobile code and browser privileges, that's why we need strict execution control. and Python, which is versatile but it is interpreted language, so we must secure the source and the scripts, dependencies, and the runtime. Our next topic is the software libraries, their purpose, their benefits. So, what are the libraries? These are pre-written code modules such as functions, classes, scripts, and procedures. They are included in SDK, that is software development kits for operating system, cloud platform, and applications. And they provide reusable building blocks for faster and consistent development. Benefits of libraries include speedy development, so we do not need to write the common functions from the scratch each time. Libraries improves the reliability, so they are widely tested and they include community refined and tested components. Enhances compliance, so they has built-in accessibility features and payment processing modules, etc. And supports system interaction, so file system access, IO handling, and device control via drivers. So security considerations of libraries include, so some of the security risk includes that there are vulnerable or malicious libraries which may impact the entire application if these malicious libraries are used inside development of the application. Then there are outdated libraries which have the known exploitable flaws if they are used. And then we have the open source libraries which must be validated and their versions must be tracked for usage inside the applications. So the best practices to use library is to always use trusted and validated libraries only, to maintain internal approved library repositories, to apply updates and patches promptly and track dependency versions, and to perform code review, integrity checks, and license compliance checks. Next is the software development tool sets. So the purpose of tool sets is that they support writing, testing, debugging, and maintaining software. They improve collaboration and consistency across development teams, and they enhance security by identifying issues early in the software development life cycle. So common tool sets or tool types include the source code editors. So they include the syntax checking, autocomplete, templates, and documentation generation. Code repositories and version control. So they include the centralized storage, integrity protection, revision history, and developer collaboration. Debuggers and bug databases, they help in identification of flaws, step-by-step code execution, and helps in tracking and resolving the defects. Then we have the compilers which convert code into machine-readable binaries for specific platforms. Testing tools and security governance. So, testing tools include static code analysis, which review code without executing it, and this type of analysis finds insecure coding practices, for example, buffer overflow risk. Then we have the unit testing tools, which verify small components individually for correct behavior. And then we have the data flow analysis that checks how data moves through functions to prevent errors or security. So security governance of toolset include that tools must be under configuration management and patch management, and only approved versions and modules should be installed and used. Developers must follow secure software development lifecycle procedures and request approval for new tools and plugins. Regular audits should be done to ensure tools support compliance and security controls. Our next topic is IDE, that is Integrated Development Environment. So what is an IDE? So an IDE is a unified workspace combining multiple development tools into a single or one platform. So IDE improves productivity, consistency, and reduces the overhead of managing separate tools. So common IDE features include source code editor, which include the syntax checking, autocomplete, and templates. Debugger, which are step-by-step code execution and helps in error identification. Build automation, which include compilers and build tools. Testing tools, which include unit test and static code analysis. Development integration, including Docker, Kubernetes, and CI/CD pipelines. And object-oriented programming support, include object and class browser and visual programming interfaces. So what are some security considerations regarding the IDE? So IDE must be approved, patched, and maintained. So a compromised IDE means overall compromised software. Therefore, only authorized plugins and modules should be installed. Then we have the runtime environment. So what is a runtime? So runtime is the full set of hardware plus software that is needed to execute an application. This includes firmware, device drivers, operating system, libraries, APIs, and interpreters for interpreted languages. So what are some security implications of runtime? So vulnerabilities can exist at any layer, that is at OS layer, drivers, APIs, interpreter, and hardware layer. So therefore, we must follow strong configuration and change management. So the interpreters may enforce the security through sandboxing and validation. So high security environments, so we need to use a trusted computing base, that is TCB, to enforce strict security policies. TCB acts as a reference monitor controlling system access. So modern runtime examples, so traditionally Windows and Mac OS plus applications were the runtime environments. In modern days, we use the Internet of Things devices such as the sensor and smart appliances and edge computing nodes. So it require secure networking such as Wi-Fi, Bluetooth, firmware, and data flows. Our next topic is CI/CD, that is continuous integration and continuous delivery. So continuous integration is that developers frequently merge code into a shared repository. It helps in early detection of bugs, conflicts, and security issues. And CI uses pull request, manual review, and automated testing as well as scanning. Then we have the continuous delivery, that is CD, where automatic code is automatically delivered to a testing or staging environment. So it requires manual approval before going live, which is common for regulated systems. Then we also have the continuous deployment, which is fully automated deployment to production after the test pass, and it requires highly mature automated, that is quality assurance and security processes. CI/CD pipeline, it is end-to-end automated flow, that is from code to test, then build, package, and deployment. And security is inserted at every stage. We have the integrity checks, encryption, and automated reviews. So testing and security in CI/CD pipeline, so automation and infrastructure as a code. So environments that are built automatically using definition files known as infrastructure as a code. So infrastructure as a code is basically the phenomena where environment or infrastructure is built automatically through definition file. So this supports configuration management, consistency, and auditability. Then we have the automated application security or AppSec. This includes unit, functional regression, and security testing, for example, SAST and DAST. So SAS is static application security testing and DAST is dynamic application security testing. So automated application security testing is faster and more frequent than manual testing. So continuous security practices include that security is integrated early and throughout the pipeline. So we have the automated scanners that feed issues directly to the developer, for example, via ticket and APIs. This reduces miscommunication and speeds up the remediation. So what is the key takeaway for this CISSP? So the CI/CD basically improves speed without sacrificing security by automating controls, enforcing consistency, and integrating security testing at every stage. Our next topic is security orchestration, automation, and response, also known as SOAR. So SOAR is a platform that orchestrates data, automates actions, and coordinates responses to speed incident detection and response. And it goes beyond just the SIEM. SIEM is security information event management. So SIEM basically only alerts while SOAR also acts automatically. So it is, you can relate it to the IDS, IPS, where IDS only alerts or logs, while the IPS also takes action. So same is the case with the SOAR. So the orchestration is that it integrates data from SIEM, user entity behavior analytics, IDS and IPS, threat intelligence, anti-phishing, anti-malware, and scanners, etc., and then correlates events into one actionable picture using APIs. For example, we may have a phishing email, SOAR links it to a user, file, UEBay behavior, and malware alert. So the second component of SOAR is the automation, which executes the playbook and machine-driven actions after alerts. So this reduces incident duration by acting faster than humans. Example include quarantining the infected machines, forcing the password reset, deleting the malicious email from all inboxes, and auto creating the incident response ticket with relevant details. So next function in the SOAR is the coordinated response. So this performs automated containment. So basically, it isolates the host, block the, you can say, source IP address or the infected URLs, run the scans, and stop the lateral movement of the infection. So humans basically focus on analysis and complex decision, not the repetitive tasks. These tasks are dealt with by the SOAR. So this produces a complete incident case file for responders. So these are some of the benefits of SOAR. It provides us with speed. So actions occur in seconds instead of human involvement, which may take minutes. It brings consistency, so it follows predefined playbooks with no delay, reduces the impact, so the faster containment results in minimized damage, and improves SOC, Security Operations Center efficiency. So it frees analysts for higher value work or task. So challenges of SOAR include that false positive can trigger harmful action, for example, locking out a legitimate user. It requires tuning to match the environment behavior and reduce errors. Our next topic is Software Configuration Management or SCM. So the purpose of SCM is to ensure integrity of software resources. such as the source code, documents, and configurations. So it applies configuration plus change management to secure software development. So the item under controls are called CIs or configuration items. So configuration items example include source code, libraries, configuration settings, page level, and requirement documentations. So configuration items must be uniquely identified and changed through a formal process. Too many configuration items result in operational delays, so we need to choose based on criticalities. So baselines are basically a stable and known good set of configuration items. So baselines are used to define secure settings, required versions, or functional configurations. Baselines are immutable, which means their changes require formal approval. They should not be changed without a formal approval or change management. Then we have the version control. So version control tracks changes using version numbers and enforces when and how new versions are created. So version control is implementing using version control system, for example, Git and SVN. So security benefits of SIM include that they protect confidentiality, integrity, availability, non-repudiation, and authenticity, also known as CINA of the software components. It prevents vulnerabilities from uncontrolled or undocumented changes and ensure visibility, traceability, and accountability in the software development life cycle. Our next topic is the code repositories. So, what repositories or repos do? So, they are centralized storage enabling team collaboration. They support branching, allowing safe and isolated code changes, and they enable testing plus merging back into the main code. The security controls in a repository include confidentiality, so which can be done through access controls such as read-write permission, restricted copying, and export of code. Integrity can be done through version control, rollbacks, controlled write access, and ticket-based permissions. Availability can be ensured through central backups, redundancy to avoid single point of failure, non-repudiation through unique user IDs, audit logs, and version history, and authenticity through can be done by verifying no unauthorized changes using version controls and backups. So protecting the repository itself. So why repo is a high value target? It is because repos contain highly sensitive data and can be exploited to insert malicious software. Therefore, it must be secured like any other critical asset inside organization. So key security controls to protect repo include data protection. Inside repo, it can be done through data loss prevention tool, IDS, IPS to monitor activity and detect the data exfiltration or code exfiltration. Similarly, we need to have the network security controls such as secure remote access using the HTTPS, TLS, VPN, and proxy so that our remote access is encrypted. Access control can be ensured through least privilege approval for access and periodic access reviews. And then we need to ensure the backup and availability of repos through robust backup strategy for the source code and build assets. So cloud repos offer resilience due to their high availability, while self-hosted repos they require strict availability planning. So we need to ensure that code is accessible when needed, even during outages. Application security testing. So why we need the application security testing? It is because security must address both the prevention as well as the active vulnerability hunting. So retesting is required due to legacy code, evolving threats, and limited resources. And modern programs use full life cycle approach. That is, the security testing should be done through all the phases as we studied during design, development, and after development, we need to carry out continuous testing during the operation and maintenance. So some testing approaches. So these topics are important from exam point of view. And the first testing approach is the SAS, that is static application security testing. So in this testing type, we actually analyze the source code and binaries without executing them, and it is integrated in the IDE, that is integrated development environment, and it provides fast big feedback, and it is safer for non-production. Limitation of SAST includes that it is dependent on language or it is language specific. It is harder for non-developers because non-developers do not understand the code itself, and it cannot detect the runtime or system interaction flaws because this testing is carried out on the source code, not on the live or production system. The next testing type is the DAS, that is dynamic application security testing, which tests running application through interfaces and APIs, and it is language independent or language agnostic and is useful for non-developers, and it is CI/CD friendly. Limitation of DAST include that routing the findings to the developer. So since developer do not do the security testing, the findings of the testing must be routed to the developers for fixing possible production performance impact. So since it is carried out on the production system, we may have the performance impact, and vulnerabilities may actually reach the production before detection because we are carrying out the testing on the production system, not initially on the source code or during development. Our next test approach type is the IAST, that is interactive application security testing. So IAST combines the SAST, DAST as well as the pen test style analysis, and it uses analytics and machine learning and has strong visibility in CI/CD pipelines. So limitation of IAST include that it is high cost, it is an emerging tech, and it has the language dependent and possible performance concern. Then we have the RASP, which is runtime application self-protection. So this type of test runs inside the application at the runtime. It detects abnormal behavior and actively blocks the attacks, for example, through virtual patching. So limitation of RASP is that it may result in false positive leading to possible denial of service, and it has limited compatibility and newer skill sets are required to run the RASP. Measuring the software security effectiveness. So why we need to measure software security? So measuring software security ensures security controls are effective, compliant, and improving over time. It is critical for protecting the applications, source code, tools, and development environments. So logging and auditing basically provides visibility into system behavior changes and anomalies. So key concepts in measuring the software security effectiveness include auditing, which is a formal review of controls and activities against standards such as ISO, NIST, and OWASP. Logging, which is recording the system events such as what was done, who did it, when it was done, and other important metadata such as source IP address, timestamp, etc. Accountability is the ability to identify who performed an action. So accountability is the who inside the log. And then we have the non-repudiation, which is the proof preventing a user from denying an action. Applications of logging and SDLC auditing. So why logs are used? So logs are used in change management to match system changes to approved requests. Logs are also important during security incidents to detect attacks, anomalies, and suspicious activities. During performance monitoring, logs are used to track the CPU, memory, and bandwidth usage to maintain availability. And in cloud monitoring, we use logs. We use provider generated status logs for outages and service issues. So guidance and standards regarding logs include the NIST SP 800-92 and OWASP logging cheat sheet. And there are some compliance frameworks such as PCI DSS and ISO that mandate detailed logging of the system. So auditing across the SDLC. So during requirement phase, we need to review the privacy impact analysis, data classification, and we need to make sure that the documentation is complete. Then during the design phase, we need to audit the risk assessments, the architecture decisions that were taken, and the residual risk acceptance. During implementation phase, the audit need to validate the code reviews, the testing carried out, the separation of duties control, and we need to make sure that proper security developer procedures were carried out. In verification phase, the audit check the overall test coverage, the result achieved, and to audit that the proper approval was taken before the deployment. And the operation phase is the ongoing audits of the live system, and this is the phase where most of the activity occurs. Risk analysis in software development. So why risk analysis matter? It is because risk exists across all the SDLC phases from initial planning up to the production system. And risk analysis in SDLC focus on to protect the assets, the likelihood and impact of the threats to the system, and the cost-effective mitigation of these threats. Continuous risk assessment is required because software environments change constantly and the risk must be monitored continuously, not at one point in time, such as yearly. So this applies to development environment, CI/CD pipeline, testing, and live production. Auditing the CI/CD environments. So modern auditing approach has moved from point-in-time checks to the continuous monitoring. And basically, automation performs the checks such as configuration scan every 24 hours or even faster as per the requirements. So in CI/CD, automated security checks basically run during the build or deployment, and if a check fails, deployment is logged. And this ensures fast delivery without sacrificing or compromising the security. So benefits of auditing the CI/CD environment include that it reduces the human errors and ensure consistent service builds because the manual checking results in mistakes and spot checks catch configuration drift in production. So what are some software development risk types? So the first one is the data risk. So the system processes sensitive data and therefore we have the high breach impact. And we need to prioritize the system by the data classification. So lower tier systems can be pivot point and therefore they cannot be ignored. This means that if a system is of lower tier, it can be used as a jump box to access other high-tier systems. So therefore, security of this system should also not be completely ignored. Second is the new technology risk. So the emerging tech has fewer controls and has less expertise. Therefore, the chances of misconfiguration are more likely due to the less expertise of the human resources. Example, in early smartphones, we did not have the full disk encryption. Therefore, the risk mitigation of losing or of a stolen mobile set data confidentiality was limited. Third is the code risk. So bugs, unauthorized changes, or malicious code exposes confidentiality, integrity, and availability of the code. And this requires code review, change control, testing, and secure coding practices. So where do the risk appear in the SDLC life cycle? So in planning, the unrealistic schedules or last minute security requirements may cause the operational risk. During requirement phase, the addition of new features may lead to internet exposure or the requirement of card payments can introduce the regulatory requirements and threats. For example, the card payment may introduce the regulatory requirement of PCI-DSS standard. During design phase, the technology choices impact control, availability, remote access, encryption, and vendor lock-in. For example, if there are some technologies that are chosen which are very vendor specific, so we may be locked in with that vendor for that specific technology. For example, another thing is the choice of the design may lead to some limited encryption availability, and similarly is the case with the remote access as well as the availability. So development, secure coding, proper tooling, and testing can mitigate the development phase risk. So we need to ensure secure coding, we need to use the proper tools, and we need to carry out the proper testing to mitigate the risk during the development phase. And operation and maintenance. So most real world risks occur during this phase because this is the phase where the software application is actually used in the real world. And during this phase, we need continuous patching, monitoring, vulnerability management, and threat intelligence. Risk assessment and treatment. So we may use risk framework from ISO, NIST, Octave, or FMEA. And during assessment, we need to evaluate the likelihood as well as the impact for each risk. And we need to develop the mitigation plans within the risk tolerance of the organizations. So risk treatment options include mitigation, which is the most common treatment plan. Then we may have the transfer mitigation treatment, which is include insurance, buying the insurance, or if the uh, environment development environment is inside the cloud, the risk treatment responsibility may be shifted to the cloud provider. We can avoid the risk by not carrying out the specific project. And lastly, we need to accept the residual risk after mitigation. Mitigation strategy consideration. So we need the cost to evaluate because the mitigation incurs cost. Mitigation strategy result in cost. So the cost may be direct in the form of tools, software licenses, consulting, and support contracts, or it may be indirect such as productivity impact, process overhead, and training. So measurement challenges of the costs is hard. It is they are hard to it is hard to measure the cost of avoiding an incident. Similarly, qualitative rating helps in this regard. For example, using the term minor versus catastrophic risk. And we need to use the industry report, for example, Verizon DBIR for reference data. So while presenting the mitigation strategy to the management, we need to show the alternative options, the cost of the mitigation, the benefit of carrying out the mitigation, and the actual residual risk that will remain after the mitigation. So we need to tie the security benefits to the business value such as usability, mobile access, and uptime. So what is the security impact of the acquired software? Another important topic. So why acquired software is harder to secure? It is because we have limited control over the development process as opposed to the in-house developed software through SDLC, and we cannot directly enforce secure coding or fix vulnerability, and therefore risk must be balanced against the cost, speed, and vendor expertise. So in acquired software, we have the COTS, that is commercial off the shelf software. So the pros of COTS is that it results in faster deployment, it has the support of the vendor, and it includes rich features. Cons include that we have no source code visibility, and we must trust on the vendor, and these cards are high value targets for attacker due to their wide use. So these cards are used by multiple organizations and clients, therefore they are high value target for the attackers. They are also vulnerable to remote code execution, denial of service, and malicious modifications. And mitigation include to maintain inventory, track vendor advisory, routine reviews, intrusion detection system, network access control, and compensating controls. Next is the open source software. So the pros of open source software is that we have the source code visibility, we have the active community that fixes any vulnerabilities or errors in these codes, and of course they are free to use and free of cost. Risk with open source software include the flaws may remain undiscovered for years even though the source code is publicly available. For example, the Heartbleed vulnerability that was found in open source SSL and that infected hundreds and millions of users. Then the malicious code insertion in public repositories. So since these repositories are publicly available, the malicious actor may insert malicious code, and once used, these repository may result in inclusions of these vulnerability inside the organization application, and of course lack of official support in many of these open source software. Mitigation of these risks include to validate the code integrity, use the official repos, to perform internal reviews, and consider commercial support options where available. Next is the third party custom contracted software. So the pros of these software is that they come with the skilled developers of the third parties that develop these software. They have the reduced project risk and faster delivery. Risks include again the loss of control over development life cycle as opposed to the in-house development, and we must enforce security through contracts, SLAs, and acceptance testing. Mitigation of these risks include contractual security requirements, code escrow, detailed SLAs, and independent testing. So, code escrow is that the source code that is developed by these third party organizations are kept with a middleman, and if this contracted third party goes out of business, that source code is then released to the client. The security impact of the shared of the acquired software in the context of cloud services. So the cloud services are basically work on shared responsibility model, which the cloud service provider handles the physical security, while the consumer are always responsible for data security. And security assessment ability basically decreases from these cloud platforms. So we have the more accessibility in infrastructure as a service, limited in platform as a service, and least ability to secure assess the security of these applications in software as a service. Again, the assessment consideration, we have the most control in infrastructure as a service because we can assess software deeply, including the operating system. In platform as a service, we have the limited control and we mainly rely on the vendor audits and SLAs. And in software as a service, we have the least control and we mainly rely on the strong assurance reports. Reports may include any of these types of reports. Audits and assurance of the cloud services. So independent audits provide confidence when direct control is lost, as we already studied, and common assurance frameworks such as these are used for assurance and audits of cloud services. So cloud providers invest heavily in security due to the shared customer base. So, secure coding guidelines and standards define and apply secure coding guidelines. So, policies are the high level direction while the standards are mandatory and the guidelines are recommended steps. So, developer must follow secure coding standards to protect the CIA, that is confidentiality, integrity, and availability of the data and the applications. OWASP and other groups provide community driven, widely adopted secure coding standards, and standards prevent outdated or inconsistent coding practices, and they are useful for auditing, scanning, and control implementation. So, what's the difference between weaknesses and vulnerabilities? So, weakness is any flaw in code or design, but it may not be exploitable. On the other hand, vulnerability is also a weakness, but there is a practical method to exploit it. So we can say that any weakness that can be exploited is a vulnerability. So all the vulnerabilities are also weaknesses, but every weakness is not a vulnerability. So some weaknesses are non-security, for example, performance and logic weaknesses, and CISSP mainly focuses on security impacting weaknesses. CWE, that is Common Weakness Enumeration. So it is maintained by the MITRE organization, and it is basically a catalog of software and hardware weakness types. And each CWE basically includes its description, relationships, introduction phase, platform consequences, examples, and its mitigation. So it is used inside the static analysis tools, training, and during secure SDLC activities. CWSSS, that is Common Weakness Scoring System. So this is used to score weaknesses for prioritization, for prioritizing their remediation. And there are three scoring groups that are used. First one is the base finding, which deal with the technical impact, privilege gained, and confidence in finding. Then is the attack surface, which include the required privilege, access vector, interaction, and scope of the weakness. And finally, we have the environmental, which deals with the business impact, likelihood, and prevalence of the weakness. Next is the CVE, that is Common Vulnerabilities and Exposure. So CVE is identifier for publicly disclosed vulnerabilities, for example, CVE-2014-1266. So this year basically shows the year during which this vulnerability was discovered, and the number is specific for a unique vulnerability. And this CVE also include its description, the affected versions of the applications or operating systems, the references, and the fixes of the vulnerability. And then we have again the CVSS, which is Common Vulnerability Scoring System. So this is used to score the CVEs from 0 to 10, which is 0 refer to none, and then it increases gradually, such as low, medium, high, and critical. So the 10th, any vulnerability that has 10 score, it means it is the most critical, while 0 has no criticality. We have three metric groups, again base, which shows the exploitability and CIA impact of the vulnerability. Temporal deal with the how mature is its exploitability, the patch availability of that vulnerability, and report confidence. And environmental is organizational specific, and it is adjusted for organization's context. So CVEs or CVSS is used via NVD to prioritize patching. NVD is a National Vulnerability Database. OWASP top 10 web application risk. So these are the top 10 OWASP web application from 2017, including injection, broken authentication, sensitive data exposure, XMR external entities, that is XXE, broken access control, security misconfiguration, cross-site scripting, insecure deserialization using components from known vulnerabilities, and insufficient logging and monitoring. So next is the security of application programming interfaces or APIs. So API is a standardized interface to system functions without exposing their inner workings. And common types of APIs include REST, SOAP, RPC, internal OS APIs, and cloud service APIs. So the REST API uses HTTP methods such as GET and POST and exposes API endpoints through URLs. So API risk includes, so their risk mainly depend on the exposure of the API. So the public API are publicly accessible, therefore they have high confidentiality and integrity risk due to their public exposure, while read-only public data have minimal confidentiality concerns because they are already publicly readable. So risks to APIs are similar to web application security because API accept and process external inputs such as the web applications and web servers. So basic authentication methods of APIs include basic authentication such as base 64 only, which requires TLS. Then we have the key-based authentication where we need API keys, which are symmetric keys used for both authentication as well as encryption. Then we have the certificate-based authentication, which may be one way or mutual, and certificate-based authentication basically requires PKI or public key infrastructure. And then the federated/SSO single sign-on, which includes SAML and OAuth for delegated identity and access. Access control must be granular, such as role-based access control list, and attribute-based control. And we need to restrict access to data and functions at the API layer. Input validation and sanitization, we need to treat all the external input as untrusted. Escaping is protecting against injection by marking content as data. Then we have the synthetic validation, which is used for the correct format of the data, for example, US phone number format. And the semantic validation is for correct values, such as valid area code. So use OWASP cheat sheet for SQL injection and input validation. So protecting resources include APIs must be threat model like web application. An example include that the Facebook view as API leaking the user tokens. Communication security of API include to use the TLS and HTTPS for data protection in transit, and symmetric and asymmetric cryptography ensures confidentiality, integrity, and authenticity. So different ways in which API is used, cryptography is used in APIs, such as for confidentiality, we need to encrypt data either pre-transit before transporting the data, as well as during transit where the secure tunnel. Integrity is ensured through hashes such as hashing algorithm of SHA-256 or SHA-1. For data verification, authenticity is done through HMAC and certificates, non-repudiation through asymmetric keys, and access control is done based on key possession. Logging, monitoring, and alerting, we need to log the authentication attempts, validation result, IP addresses, and timestamps, and we need to forward logs to SIEM solution for monitoring, correlation, and alerts. So API security testing, we need to use functional security and performance testing depending upon the risk. And tools used in testing depend on the API type, such as the REST or SOAP API, and OWASP API security project provides guidelines and top 10 API risks. Secure coding practices and standards. So why we need secure coding? It is because secure coding prevents flaws, bugs, and vulnerabilities, and it requires standardized, documented, and organization-wide practices. So CISSP role in secure coding is to define requirements, validate controls, but not write code. So CISSP do not need to understand the code or write the code. Security culture essentially include clear policies plus supporting procedures, guidelines, and checklists, training and awareness of all roles, and to align security with organizational goals. The core principle of secure coding includes to have the secure by design principle, which include embedding security at the very initial design phase and to always assume attacks. Secure by default is the conservative settings of least functionality and private by default. DevSecOps is to shift security to the left and integrate security into CI/CD. Security shifting to the left means, so if it is the timeline, Shifting security to the left means to start security from the very beginning or during the initial phases, such as during the initial design or planning phase. Building security in software assurance maturity model and BSIMM. So mature secure development through metrics and practices. Next is a software defined security, that is SDS. So SDS is a virtualized software controlled security replacing hardware tied tools. SDS uses software defined networking plus automation to apply consistent and portable controls. And benefits of SDS include enhanced availability. So control basically follows the workload wherever they go across all the locations. Infrastructure neutrality. So one policy applies to all type of operating system and different types of cloud platforms. Micro tagging is through automated microsegmentation and fine-grained rules per workload. Centralized management is used for unified view of policies across all systems. Automation and dynamic response, so sword-like orchestration, self-healing, and rapid mitigation, and supports modern architectures such as cloud, microservices, and API-driven systems. So that's all for this domain as well as the course. I also have the practice question for CISSP on all domains. Each domain has 50 practice questions and overall 400 practice questions, which are very handy. And you must go through all these questions as well to prepare yourself for the CISSP exam and identify your strong and weak areas. So that's all. Please, if you have any query or question, write in the comment and I will happy to reply. See you in the next course and in the next video. Thank you for going all the way through this course and through all the videos. I am very thankful for your patience and for watching all the videos.